Welcome everyone to this lecture on sequence modeling. So first of all, what are sequences? What do we mean when we talk about sequences? There are two main types. There are probably more, but the main things I want to mention fall into these two buckets. So first of all, time varying signals. And so some common examples of that would include the audio signal, for example, human speech or music or animal vocalizations. Secondly, another good example of that would be recordings of brain activity. So things like EEG or MEG, which are two ways of recording signals related to brain activity, electrical signal and magnetic signals. And so these have applications in neuroscience especially, and are often processed using some kind of deep learning, including recurrent neural networks. And thirdly, just time series in general. So time series are data where each data point is not seen as in isolation, is not drawn independently of all the other data points, but rather they're arranged in a time series, in a temporal sequence, one coming after the other. So this could be a lot of different types of data. Something like a simple example would be the recordings of a temperature at a particular location in a particular span of time, for example, during 10 years. Another example would be the prices of particular series of stocks on the stock market. So in the first case, in the case of the temperature, we would have one-dimensional data because we are focusing on a single location and a single measurement, which is temperature. In the second case, we would have a series of stocks, some number of them, and so for each of them there would be a particular price at a particular point in time. So we would have multidimensional data in that case. And similarly, for the other type of data, for brain activity recordings, this would also be typically multidimensional because there are a variety, like a number of sensors associated with a particular location around the skull, or a location in the sensing equipment. For something like audio, it's a bit more complicated. It depends how exactly we represent the audio. Typical way of dealing with audio would be to first convert it into some kind of extract some kind of features, such as so-called band frequency substroke coefficients. So these would be also then multidimensional data because there is a number of those coefficients that we're extracting. But audio can be represented in other ways also, in the form of spectrograms. In that case, again, we have something multidimensional, or it can be thought of as multidimensional. A spectrogram is something like looks a little bit like a two-dimensional image, where one of the dimensions corresponds to time and the other one corresponds to frequency. And the other type of sequential data that we may be interested in dealing with using sequence modeling in deep learning would be discrete sequences. So these are simply sequences which are symbolic in some way. So text, these are sequences of letters and similar symbols. Mathematical symbols would be another type, which are often combined with text. And if you read a scientific paper, there would be both of these types of symbols together. With mathematical symbols, it's a little bit also complicated. It can be complicated because they can have two-dimensional structure. So they at least the way that they are typically visually arranged on a page for humans to read, the location is not strictly sequential. It's also it's two-dimensional, but they can be linearized. And when they are linearized in some way, then they become a sequence. Another type of discrete sequence that we may be interested in dealing with is something like DNA data. So these are often represented in terms of a sequence of bases of 4 bases that DNA consists of. So when dealing with discrete sequences, we need to represent them somehow in some way which is appropriate for the neural network models to deal with. And so we have either letters or we have words. We have these discrete units, and these need to be converted into some kind of numerical representation for the neural models to be able to understand them. And so there are 2 types of representations which are commonly used. One of them is very simple. It is known as one-hot encoding or one-hot vector. And what we have here for each symbol, we will have a vector. And this vector is going to be the same size as there are symbols in our alphabet or in our vocabulary. So as many symbols we have, that many dimensions will be in this vector. And one of these dimensions is going to be set to 1, and all the others are going to be set to 0. So the one which corresponds to what the current symbol is going to be 1, and all the others are going to be 0. So this is similar to something known as dummy encoding in statistics in general. However, this is appropriate for things like with a small number of types of symbols. So maybe it's a reasonable type of representation for something like 4 bases of the DNA, or like whatever 20 to 40 letters of a typical alphabet. But often for like we're dealing with words or with some word fragments like morphemes, then we will often use a different type of representation which is not one-hot, and it's known as an embedding representation or embedding vectors. And so these embeddings are typically smaller in their size than our vocabulary is. So let's focus on the case where we're dealing with embeddings of words. So we may have, depending on our data set, many thousands, tens of thousands, sometimes even hundreds of thousands of different words, and we do not want to have embedding vectors which are that large. That wouldn't be practicable. So what we'll do is that each word is initially assigned to a unique random vector, so just simply randomly initialized, and our vector is going to be smallish in size, so it may be 300 dimensions or something like that, much smaller than the number of words that we have. And then these are initially random, but then they are updated during training together with all the other parameters of the model. And so what typically happens after the training has progressed is that similar words will end up having similar embedding vectors. And so this is similar to just something that you may know already from elsewhere, like a word-to-vec type of representation for words. This is very similar. It's the same idea. It's just these vectors are now trained within the larger neural network, where we are training it using some particular task, and as a side effect we are also creating these word embeddings. So a question is, why do we need something fancy for this sequence data, or do we actually? So can something like an MLP or a CNN be applied to sequence data? Well, the issue is that, yeah, in principle, they could, but these data that we just mentioned, like text or audio, they are often of varying length, and they are not easy to resize. So also images can be of different sizes, but it's kind of relatively easy in most cases to just resize them, resample them so that they have the same size and just work with a fixed size of data in the case of images. For the case of something like text, maybe it's sometimes doable when these are like just very short pieces of text which we can just pad to some kind of length or something. But in general, it is much less doable. So we will typically want to have a type of model where we do not require a fixed size vector as input. Another issue is that convolutional neural networks have something called a receptive field, and that also has a fixed size, which means that if we want to capture dependencies between points in the data which are far apart or are larger than this receptive field, then we will need we need to increase the number of layers, and so what we have in language or in audio often are dependencies between points far apart in the signal, and these can be non-trivial to capture with these type of models that we've seen so far. And thus what we will look at today are recurrent neural networks, which are a specialized architecture specifically designed to deal with sequential data or with time-varying signals. So how does this work? So what we do with recurrent neural networks is that we have a hidden layer, like in other types of networks, but this hidden layer changes over time. It's not static, and crucially it is updated based on the current state of the signal, but also on its own previous state, and that is known as recurrence. So we will see the details in the next few slides. So the most basic type of this network is known as simple recurrent network and was introduced in these two papers by Ellman. The first paper is from Cognitive Science, Finding Structure in Time, and the second paper is from Machine Learning, and it's titled Distributed Representations, Simple Recurrent Networks and Grammatical Structure. And so Ellman is passed away recently. He was a professor of cognitive sciences at University of California. He was interested in as the titles indicate here, in sequential data and especially in language and in grammatical structure, and he introduced these networks to capture these type of phenomena. This is like a graphical representation of what a recurrent neural networks looks like. So in the lower part, what I have indicated here is the input, and that you can think of it as a one-hot vector or something like that, which represents the current symbol which is being processed by the network, like the current word or the current letter. And then in the upper part, what we have is the state of the hidden layer. So this hidden layer in this very simplified example has 3 dimensions, and it's all of them are connected with these arrows to the input. So you can see that what that indicates is that the activation of the hidden layer depends on the current input, and there is also this looping arrow with a black rectangle on it that is meant to indicate a recurrent connection. So a connection which links to itself with one time step of delay. So what it means is that we take the activation vector of the at the previous time step or at the previous position in the sequence, and the state of the hidden layer at the current point in time also depends on that. That's what this looping arrow is meant to indicate. And so this looping arrow, both of these arrows, which are from input to hidden, and this looping arrow, which is hidden to hidden, these are weights, right? And these weights are learned during training. The crucial thing about the recurrent neural networks is that the hidden to hidden weights are shared across time steps. So at every time step, we have the same set of weights that we apply always. These weights are updated during training, but between time steps they're reused. And so, what is exactly the mathematical formula behind these arrows? Well, what we have here is this equation where ht represents the hidden activation vector at time t, and then you can see that it depends on ht minus 1, so on the previous activation vector. It also depends on xt, x being the input at time t, so the current time. And it also depends on these parameters, w, u, and b. These are simply weight matrices and a bias. And there is also a function sigma, which is some kind of sigmoid or a tanh function. And so we typically initialize also this hidden state, the state of the hidden layer. It needs to have some initial state. We can simply initialize it to randomly, or to zeros, or to some or treat it as a learnable parameter. There are various formulations. Yeah, so just to kind of spell out the notation, W in this formula stand for hidden to hidden weights, U stand for input to hidden weights, and T is simply the index of the time or position in the input sequence. So so this is just what we've seen so far is how the hidden state evolves over time as a function of itself and the inputs, but we haven't really talked about what we're trying to learn. What is the target that we're trying to predict? And so that is important, because that is what drives the learning and how the weights are updated. So there are a number of scenarios that we can think of. So the simplest case would be that there is just a single target, a single output that the network is predicting based on a sequence of symbols, or on a time series of or on a time varying signal. So we could be doing like a simple regression or classification, but with a recurrent neural network. So a sentiment analysis on text would be one example. We are just predicting whether like a binary classification, whether the text has a positive or negative sentiment. Another example would be speaker identification on the speech signal. So we are trying to predict which of a number of a set of speakers is uttering a particular sentence or a particular stretch of speech. Or a classification of percepts with EEG or MEG. By percepts, I mean what we would record what people are perceiving, for example, what they are watching, what they are seeing, while recording their brain signal, their brain activation, and then based on this signal, we could be predicting that with a machine learning model, such as a recurrent neural network. So that is the case where we have just a single output for the whole sequence. Then there is another scenario where we will have like one output per time step or per position. And so these are especially common with computational linguistics type of research or models. So one example would be something called part of speech labeling, and that task consists in predicting the part of speech or the grammatical function of every word in a sentence. So is it a noun, is it a verb, is it an adjective, and so on. And that is something that is sometimes is useful for linguists. And so if we have a data set where each word is annotated with such a label, we can use it to learn to predict those labels for new data for unseen sentences. One important example for this scenario of predicting something for each time step is predicting the next step in a sequence. For example, in the case of text, we might want to predict what is the next word coming up, or in sometimes we might want to predict even character by character what is the next character. So this has some practical applications, some kind of direct applications. For example, in predictive typing, when you're typing something on your phone, maybe it helps you by suggesting what is the next character or what is the next word or next couple of words that you want to be entering. But it also is useful as a so-called self-supervised model, in the sense that when we're doing that, when we are training a model to predict the next step in the sequence, it learns representations which are often useful in all sorts of other ways. We will look into that a bit later. And the final scenario is a bit more complicated in a sense. What we have here is that our output is another sequence, is a whole other sequence, and it's not like you could also think, that when we doing part of speech labeling, we are also just predicting a sequence of part of speech labels, but that is that has a very restricted structure. We know that for each word we want to predict a single grammatical label. For the cases that I mentioned here, such as translation, this is not the case. If we're doing translation, there is no one-to-one mapping from one word to another word in another language. We're just translating the whole sentence or the whole paragraph into a whole sentence or paragraph in another language, and these words are typically going to be in a different order. They sometimes one word corresponds to multiple words in the other language, or vice versa. Some words are not, don't have a corresponding translation at all. So it's all much more complicated, and much more complicated mapping. And similarly, slightly less complicated in the case of speech recognition, or transcribing speech into written text, into letters. In that case, we usually don't have too much reordering. Like, so if you have a particular stretch of sound, like, I don't know, dog at the beginning, that will not end up at the end. It will, the letters D, O, G are going to be closely are going to correspond to the location of the corresponding sound, but still it's not like a fixed. We're not mapping each frame of the input into a single into a single output. So how do we do that with a recurrent neural network, with a simple recurrent network? So basically, we just need to this formula, sorry, which we had previously, which described the evolution of the hidden state. We also need to add how we're going to obtain the target, and this is what is here in the third line. We have this y, which is our target, and then we have we see that it depends on the hidden state at time n, and where n is the index of the last time step. So we are predicting based on the on the final state of the hidden layer, and it's also this is passed through the weight matrix V, or projected with the weight matrix V into another vector, and V are simply they are known as hidden to output weights. So it's another set of learnable parameters. And F is going to be an appropriate activation function. So depending on what exactly we're doing, whether it's classification or regression, we're gonna use a particular activation function that we will need. And those you should already know from previous lectures. But just to give you an example, if we have something like age prediction, well, F in this case would typically be something like simply either an identity function. So we would just use the number that comes from applying the matrix V to the hidden vector Hn, or we could maybe use something like a rectify a linear unit, because we know that age is never going to be negative, so we can use that information. And for the case of sentiment classification, we would use something like a sigmoid, for example. So how are we going to do this with when our outputs, when we don't have a single output, but we have an output for each time step? Well, the idea is roughly the same. The difference is that we don't have a single output y, but y is now indexed by t. So for each time step or each position in the sequence, we need to have a prediction. But what we will typically do, we will have again a single hidden to output matrix, which we reuse at each time step, and we project the hidden layer at each time step ht. We project it using this matrix, and then apply the appropriate activation function. So we haven't talked about how to output a whole sequence. We will talk about it a bit later, but now I wanted to mention some other types of recurrent neural networks. And the reason for this is that simple recurrent networks, they were popular for a while during shortly after Elman introduced them, but currently they're almost never used as in their original form. They are hard to train to capture long distance dependencies. So I mentioned that the motivation for having something like a recurrent network was, one of the motivations was that you want to be able to capture long distance dependencies. But it is, and then in principle they can do that. They are able to do that. They have the expressive power to achieve this, but they're hard to train to do that from data. So they will typically learn to capture things which are spaced closely together in the data, but they will not typically fail to learn dependencies in the data which are widely spaced out. And mostly it's to do with the way that these gradients flow in these networks when we do backpropagation. So there are two problems, two opposite problems, and the gradients may become very small. This is called the vanishing gradient, or they sometimes may become very large, and these are called exploding gradients. So if you do this backpropagation through a recurrent neural network, that is known as backpropagation through time, and due to these problems, the training can become unfeasible for many types of interesting problems. And for this reason, we typically don't use these days. We use if we use recurrent neural networks, we will use something like a long short-term memory typically. And so these are network. Let me just maybe explain why this name, long short-term memory. So you can think about network weights as a sort of long-term memory. Long-term in the sense that this is we're learning it over in the process of learning patterns from the data. So this is what we learn with backpropagation. The network stores what it learns from examples in these weights in the same way that organisms such as us store memories from events that happened in the past in the long-term memory and other types of knowledge. The evolving hidden state that recurrent neural networks have, you could see it as analogous to short-term working memory, which stores information which has to be kept around, but only briefly. So what happens in this hidden vector is that there is some information in there that may be useful for the task that a network is trying to achieve. Let's say predicting the next word. It may keep some information about what happened at the beginning of the sequence in order to be able to predict what is going to happen at the end of the sequence. So this is some evolving state which is analogous in some way to working memory, to short-term memory that we use also when we trying to produce a sentence or understand what someone is saying or do some calculation or do something like that. And so the architecture called long short-term memory enables the hidden state of the recurrent networks to span over long sequences, and it improves the issues with vanishing gradient. Okay, so it is called long short-term memory because the short-term memory becomes is able to capture longer-term dependencies due to a particular way that things are set up in this architecture. And so these types of networks were introduced in this paper from '97 by Hochreiter and Schmidt-Huber. And this paper is from Neural Computation. And you have the pictures of the first two authors. The one on the left is Hochreiter. The one on the right is Schmidt-Huber. And Schmidt-Huber is still an active researcher in deep learning. It also has some quite controversial views. So if you're interested, you might want to check him out. And so this is the representation, the graphical representation of what LSTM so-called cell looks like. An LSTM cell is simply a single unit that deals with information at a single time step. And so the main idea behind LSTM is that it has a number of gates, and so these gates control writing or keeping or erasing data from the hidden state. And these gate activations are learned. So these gates are units with which typically have they are meant to behave like logic gates, but they are not completely binary. They have some kind of sigmoidal function applied to them, and so this whole architecture is still differentiable. So gradients can flow through all these. We can do backpropagation through these things. That you also have here a link to a video by Geoffrey Hinton, who explains the LSTM architecture if you want the details. So what are gates in a bit more detail? So gates are what are basically vectors which are applied via element-wise multiplication to other vectors. Okay, and so in this sense they can be said to control writing or keeping or erasing data. So in this example, what we have here is this vector ABC. Let's say that this is some data that we want to manipulate in some way. and there is a gate which is this in this case it's like a purely binary vector with zeros and ones. As I mentioned, in reality that's not necessarily always completely binary, but for simplicity I made it binary here. And so what we're going to do when we apply this gate to this vector ABC, we're going to multiply these two vectors element-wise. So the resulting vector is then A0C, because the 0 in the second dimension, when it's multiplied by B becomes 0, the others are kept. So you can see that with this gate, what we decide which elements of the vector we're applying it to we want to keep and which ones we want to remove or erase. And so for that reason, this is the reason I mentioned before, that gates can be seen as approximations of logic gates, either letting information pass or blocking it. And so let's look at the gates that LSTM has. And so it has a forget gate, an input gate, output gate, a memory cell, and a hidden state. So you see there is a lot of moving items here, and it can be a bit overwhelming, but there is some logic to it. And so you can see that all these gates have a are defined in a particular way. So let's first look at the forget gate. So the forget gate depends, and the notation I'm using here is a bit similar to what I was using for SRNs. So XT stands for the input at time t or at position t. T minus 1 stands for the activation vector of the hidden layer at the previous time step, and UF, WF, and BF are learnable parameters, so they're the weights and the bias, and the F here stands that distinguishes them from other parameters which are associated with other gates. So these parameters UF, WF, and BF are associated specifically with the forget gate. And then we have the sigmoid activation function to make sure that that this gate is a vector of numbers close to 0 or 1. And so the forget gate allows us, when we will see then how we use it in the memory cell. We have the other two gates defined in basically the same way. So input gate and output gate, IT and OT, and these are defined using their own parameters. So UI is associated with the input gate, UO is associated with the output gate, and so on. And then finally what we have is the memory cell, and the memory cell is also something that what is worth maybe mentioning, that for LSTM we have in some way we have like a two things which change over time. One is the state of the memory cell, and one is the hidden state itself. And so there is like a partitioning between these two vectors. So the memory cell is defined as the summation or weighted sum of two terms. The first one is the state of the memory cell at the previous time step, modulated by the forget gate. So you can see that we take the previous state of the memory cell, we apply the forget gate to it in order to forget some of the information, and this part is summed together with another term, which is one of those is inside this tanh activation function, and that depends on the previous state of the hidden layer and on the current input. So this is analogous to what we saw with SRNs, right? So this is what goes into the memory cell, and that is modulated by the input gate. So again, we may want to keep some of the dimensions zero out some other dimensions, and these two terms are summed together. And finally, the hidden state is updated based on this memory cell, what is in the memory cell. We apply the tanh activation to that and modulate it with the output gate, which again has yet another opportunity to forget some things and to erase some things and keep some other things, some other dimensions from this memory cell. And so one of the reasons that this works better than SRNs is, all these additional complications have some rationale. One of the intuitions behind it is that the memory cell, what we have here is this weighted sum of two items, and so the memory cell current state depends on the previous state of the memory cell in a relatively simple way, in the sense that there is it's just a part of a summation. So it's like and that means that the behavior of the gradient is better in this particular case, because the current state of the memory cell is partially determined by just taking the previous state and summing it with some other term. So let's look a bit at how we can simplify this whole concept. So we can just wrap it up into a single function which we will call LSTM. And this LSTM, what it has as input is a function which takes as input three things. It takes the so this is a function which tells us how to update the state of the hidden state, how to update the hidden state and the memory cell, and it takes the current input, the xt, the previous hidden state ht minus 1, and the previous state of the memory cell ct minus 1. Okay, so you can see that the current hidden state and current memory cell depend both on current input, hidden state at the previous time step, and the memory cell at the previous time step. So LSTM, this function, takes these two things, combines them together, and outputs the new hidden state and new state of the memory cell. That is LSTM in a nutshell. So that's a lot of detail, and the first time you go through it is probably a bit overwhelming, but go through it a few more times, and you will see that there is structure behind it, and you can encapsulate it in this main idea that I depicted here. That we just have a way of updating HT and CT based on the input and on what happened in the past, and that's what makes it yet another version of a recurrent neural network.